So now that I give an overview of closures and gave a hint about how to implement them using Java Lambda expressions, let's walk through the case study ex6 in more detail. And this particular example will apply closures, Lambda expressions, and Java thread objects to create public and private RSA keys concurrently. And you'll be able to find this code in the ex6 project in my FP folder in my modern Java GitHub repository. So here we are in the ex6 project in that folder. Let's go take a look at this program. As I mentioned before, this shows how to use modern Java Lambda expressions to create thread closures that we then use to check the primality of large numbers as part of computing public and private RSA keys. So here's the main program. This is pretty much what we just looked at. We're going to look at it in more detail now, though. So you can see that we go ahead and we create two instances of the check primality class. That, of course, is the key thing here that's showing the closures. So let's go ahead and take a look at that class. Here's the class, check primality. You can see it has a pair of fields, m prime result and m thread. M prime result is actually a Java record. Java record is a type that was introduced, I believe, in Java 16, and it allows you to have data-centric objects instead of having things that are traditional Java objects that contain other fields that are hidden, things like a virtual pointer and an intrinsic lock and an intrinsic condition and so on. A record just contains plain old data. So here we have a prime result record that contains a big integer field and another field that's a Boolean, which is going to be recording whether or not a number is prime. So that's what the prime result is. Let's take a look at make thread closure. This is where we actually do the closure. You can see we make a new thread, and that thread has a Lambda expression, and it basically captures the value of n that's passed as a parameter. That's the number that we want to use here to check its primality. And in order to do this, we call the prime utils check if prime method. And this particular method uses another helper method that's defined on big integer called is probable prime, which will give you a probabilistic result. Now, if you want something that's going to be even more deterministic than this, you can write a piece of code that will actually check to see if the number is prime. I didn't do that here, but it's easy to do. This is also way faster. And when you start dealing with gigantic big integers that have 1024 bits of resolution and precision, it takes forever to do them with a classic, slower way of computing whether something's prime. So you can see here we check to see if something's prime, then we make a new prime result that indicates the primeness of the prime candidate. So that will take place in a background thread. We make the new background thread here and make thread closure. Here's the check primality constructor. We give it the number. We make the thread closure. We store that in the mthread field. Here's the start method. It starts the thread and returns the object so we can chain it together in a fluent interface style pattern. And then finally, we have the getResult method, which just calls the join operation on the thread object, which acts as a barrier synchronizer and will not let the control flow any further until that thread continues or until that thread finishes its computation. And then we return the result. So that's the check primality class. We'll generalize this later to implement what's called an active object, but that comes later in the course. You can see what we do now is we chain the result of creating the check primality object to make a started thread. So we go ahead and start the execution. That gives us back a check primality object, which will be running in the background at this point, checking to see whether the prime is going to be, whether the number is prime or not. Here's how we generate the probable prime. In addition to being able to check to see whether something is prime probabilistically, big integer also has a method that probabilistically generates a prime number with this many bits giving a particular random number generator here. So this is going to generate a very, very, very large probabilistically prime number. Once we do that, we then go ahead and let those things run. We call getResult, which as you saw will block, waiting for the results to finish, for the computations to complete in the background. We get those results, store them into these two prime result variables, and then we go ahead and print out the values, indicating whether they're prime or not. And then the final thing we do is we go ahead and we generate the public and private keys using those values, the prime values that we got back, assuming that they're prime. And here's how we do this. This basically just does a very straightforward implementation of the public and private key algorithm, which follows this particular notation here, formula. And we do that by multiplying the two numbers together to get the modulus. We create a public exponent, which is given this value, which is commonly used for the public exponent. We compute the private exponent by doing some math here with big integers. Then we go ahead and create the public and private key specs. And then from that, we go ahead and generate the public and private keys. So that comes back as something that I call an RSA key pair. That is also a Java record. So that this is going to have the public key and the private key. And we want to be able to do that so we can have a single result that comes back here that is then used in the program to generate the public key and the private key. So given all that, let's go ahead and run the code. You'll see again, we did the probabilistically prime mechanisms here because it would take a very, very, very long time to check to see if this absolutely enormous number is prime or not. So this particular approach figures it out pretty quickly. And then it gives us the public key and the private key, which is shown here. So that's just a quick walkthrough of the ex6 example, which demonstrates how you can use Lambda expressions in order to be able to implement closures and do them in a way that can run in a thread context to do the computations in the background.